I should introduce myself. My name is Luckhaus. I'm currently we call that senator for mathematics of our National Academy. And I tried 1 month ago to explain already in a German YouTube video what mathematical epidemiology says about corona, says about the notion of herd immunity. And unfortunately, this video didn't get much traction. And now I'm trying to have it in slightly shorter pieces and in English. And I'm trying to be not too mathematical, but some of the episodes will be mathematical. So I will explain whenever things get more mathematical and when they do not do this. So the first episode I called SIR models and data. The two letters SIR have the following meaning. This capital S is the number of so-called susceptibles. These are the individuals who have not yet been infected. I is the number of currently infectious individuals. By this, I mean those who have been infected, who are still infectious, so I mean their infection is still going, and who are not in quarantine, right? So it is important so that they are able to infect others, right? And R is just the rest. I mean, it's we call that removed. Removed originally meant either immune or dead. And here, as I'm explaining, it means either immune or quarantined or dead, of course. And so this is the kind of model that I'm going to speak about. I want to make the connection with data. And I should say that what we are trying to model here is actually the course of, or let's say the epidemic course of such an infection like corona. By this, I mean the number of currently infected people is fairly high, so that we can use mathematical machinery on it, which I'll explain just on the next blackboard, which I already prepared. So let me briefly tell you about that. So as I'm saying, put this up a little bit. Okay, maybe. Well, it's always, let's put it this way. Okay, so there is the total number of individuals, which does not change. So we are not looking at the process of birth, for instance, or people coming to a country or something like that. And in the quantities that we are actually looking at is the relative percentage of susceptibles, infectious, and removed. And we write down a system of what we call ordinary differential equations for this. And I will try to explain what these strange Greek letters mean. So the basic, I mean, those of you who have listened to a course on in calculus, of course, will know what this means. And those who did not, maybe the best thing to explain what is happening is a little bit like a chemical reaction. So you have the number of susceptibles, or the percentage of susceptibles, that is decreasing by the infection, because the infectious people can meet susceptible, and there is kind of the process of infection itself, and the kind of probability per time to meet that infectious person. That is kind of what is contained in this parameter alpha. Alpha is just a parameter in this model. And then you have in this model also the rate, that is the other part of it. So you have a rate at which infectious individuals are removed. So being removed could be taken into quarantine. So that would increase this better, or it could just be that the course of the illness comes to an end after 4 weeks or so. You are not, well, in some cases longer, but after a certain period, the infection, I mean, the illness will be over. You will be over the infection, and you will be at least temporarily an immune person. And both kind of effects are hidden in this removal rate beta, which you have there. If there is no quarantine, then the removal rate would be more or less the same as 1 over the length of the infection per individual. Now, when you look at these 3 equations which we have there, these equations, of course, are trying to explain, that's what this strange dt means, they are trying to explain what is the rate per time of change of these percentages, S, I, and R. And this is a very old kind of model. It's something like 100 years old, and it explains a little bit this, what I write down there in this term as a picture, right? So it explains what is, we call that the trajectory of an epidemy. So let's say we start with what I would call a virgin population. So everyone is susceptible there. So this little s is equal to 1. And then when you, what is going to happen is, of course, a small rate of infection somehow is usually imported from the outside. And then the epidemy starts. Now, the epidemy starts, so in this model, the number of susceptibles always decreases. When while this number of susceptibles is decreasing, at first the number of infectious people gets up, but then it gets down again. And that is because in this quantity here, you have these 2 terms. You have this alpha s, and you have this term beta. And if alpha s is larger than this beta, things are increasing. If alpha s is smaller than beta, then the number of infections is going down. And the rate, now I see that I made a mistake. That is very, very the same as always. It's not alpha over beta, it's beta over alpha. Sorry. So beta over alpha is actually the beta over alpha is the value of S of the number of susceptibles, or the percentage of not yet removed in the population, at which the number of infections is always starting to decrease. So what does this actually mean? What does this, what do these little arrows and trajectories mean? They mean if you are starting at any kind of, at any percentage of susceptibles, which is still larger than this beta over alpha, then somehow a small perturbation, so any small number of infected individuals that you introduce from the outside will lead to an epidemy which will run its course up to the so the infections will increase up to this point where the parameter S reaches the value beta over alpha. And that value here, beta over alpha, that is what we call the herd immunity. So if your population has a number of susceptibles which is already smaller than beta over alpha, it is no longer possible for the epidemic to start again. If it is, the epidemic can start again at any time. And that is the basic kind of what I will call the basic result of this very simple sort of equations, is the simplest or basic SIR model. Now, I should make one remark here that is important. What I'm drawing is just during this course of the epidemic, I'm just drawing what we call in the phase space, I'm drawing the relationship between infectious and S. What I'm not drawing here is time. So if you go to a different way of representing your infection, not the relationship between S and I, but actually the development in I, the development of I in time, then you will get a completely different picture. And I will just, well, I have to erase what I wrote on the blackboard here and explain that picture and how it relates to the data that we observe just now. So now you see I was able to clean the blackboard, and I'm trying to show what you see in the data. So what corresponds to what I call the trajectory, which is kind of this epidemic course or course of the epidemic, what corresponds to that in the data which are usually shown. So usually you are shown, I mean, the number of newly infected per time, per week or something like that. And typically during the course of such an epidemic as we had now, this is the course that you see. So you have something which initially looks a little bit like an exponential function, and which is increasing. But then, of course, at some point you reach a level, and the thing is decreasing again. So the level which you are reaching here in the theory should correspond actually, and I will just draw this back and show it on the other side. It should correspond to the highest point here on the trajectory. So it should correspond to the value S equal to beta over alpha. So that is the kind of thing which you can get from the data. So there is a relationship between this beta over alpha and the curves which you see here. Of course, the curves are usually not so nice as they are seen here, but I mean, it should be something like this. Later on, I will explain why, unfortunately, there are defects in the model which makes this simple relationship, which I show here, actually not quite so simple. So it is not quite so simple to make to look at the graph that you see here and get the corresponding herd immunity factor beta over alpha. So that was the first thing that I wanted to tell you. Now, the other thing that I wanted to tell you is, of course, it might be that actually this value beta over alpha is actually larger than 1. That means alpha is smaller than beta. Now, in that case, you don't have this picture. So there is no epidemic and you are in good shape. Now, how is, I mean, when do we have one situation, when do we have the other situation? Now, what we can roughly say is, and that is the example of that we have seen, I'm going to explain that later on. What we can roughly say is because the Icelandic administration was able to somehow to stop the epidemic by quarantine methods, which were applied basically to everyone who was considered being in contact with an infectious person. So if this kind of quarantine is done on the scale that the administration in Iceland was able to do, then actually it is beta is so, what we have here, the beta is so strong that it is actually, that beta over alpha will be actually less than 1, and you will have no epidemic. That is, or the initial kind of number of infections will always go down. So you're always on that side of the curve. On the other hand, we know that if we do it with the quarantining methods and the amount of testing which this involved, which we have here in Germany, or which we had in Iceland at the beginning of the epidemic, then it is certainly true that beta over alpha is not larger than 1. So beta over alpha is less, in that case, less than 1. And that means that we are in this, for s equal to 1, we are always in this unstable situation. Now, so in other words, so we are somewhere here on the curve with a fairly high, let's say, level of immunization. And I will argue that this level of immunization here in Germany should be something like maybe 5% or so. In other places, of course, it is different. Now, I'm going back to this newly prepared backward, and I will tell you also something what is not so interesting now for Corona, but which has been also observed about this SIR model. So you can even use it to explain something which is what we call the endemic state of an epidemic, and that is done by perturbing a little bit the system by assuming that you're going to a longer time scale, and on this longer time scale you have new susceptibles coming into the population. That means that here, if we are looking at the rate of change of the susceptibles, this is no longer only negative by the new infections, but there are so-called newly entrant ones. Well, I mean, the removed, in other words, and will produce offspring. And so one way to do that is I'm changing a little bit. Epsilon in mathematics always means something small, changing a little bit the equations. And what you see then is above the level which is given more or less by epsilon, above that level, nothing much changes about the form of the trajectories. And I draw this form of the trajectories as what we call the fast trajectories. That's really the epidemic trajectories. But what is changing is, of course, that now you have a slow motion, which, for instance, if you start for any s, will move you, and I equal to 0, will move you to the value s equal to 1. Just because, I mean, here you have a positive term sitting in there. And what this means now for the equation, it means that you are going to have what we call a singular perturbation. So below this level epsilon, there will be actually a slow movement. There will be a fast movement above, but there will be a slow movement below this level epsilon. This will have the effect of what we call a relaxation oscillation. So it's a kind of like an oscillatory kind of behavior. There are always new epidemics coming up till you have come to something which is then the stable state of the system. And this system has only one stable state, and it is given by a value for the infections, which I wrote down here, which is approximately epsilon. So it is small, but it is not zero. So you have a final state, what you converge to, which would be an endemic state with the same actually level of immunization that you had, that with the level of immunization, which is actually the herd immunity of the old system, but now with a small small infectious endemic infectious rate, which I called here epsilon star. Okay, so let me at this point make a stop. So that was all I wanted to say today about the basic SIR model, how to interpret that. And I will say a little bit more about the way that we even, you could say, derive an SIR model, or I should say, the way that you see how this kind of type of equation, which is just an equation which gives you rates of change in time, how this comes about in starting from other models, which are completely different in type, which are models which tell you that you get infected, that as an individual, you get infected at a particular time. And how these models are coupled together, that will be the content of the next episode. So thank you for your attention.